Alrighty, lads and ladies, welcome back to the wonderful world of college algebra. Let's get right to the punch today. We have recently been talking about exponential functions. And most recently, we introduced the concept of a logarithm, but only in these kind of loose terms. So today, what I really want to do is, one, make sure you are as comfortable as possible with exponentials. Two, review certain properties of inverse functions. And three, give you a very concrete look at the logarithm. So this is MAC1105, section 15 of 015, which is college algebra. And the date today is the 29th of March, 2022. I believe it's the 29th. Yes. Okay. Like I said, the aim today is to ensure comfort with exponentials. We did end up extending that exponential homework, that last one, for the whole class last week. So hopefully that was sufficient. But if there are any lingering questions here, today would be the day. We're going to briefly review the concept of inverse functions. And then finally, we're going to give a concrete introduction to logs. And not that we defined them in some way that is somehow not concrete last time, but I want to give us lots of practice, straight up evaluating logarithms, share some resources that I have for you, and perhaps issue a warning about the algebraic properties of these functions. So let's start with that first item. Is there anything relating to the exponential homework that you guys have been working on that we'd like to take a closer or more careful look at? Okay. Yeah, I do see one request here in the chat. And is that all right? Yes. So we want to look at number 12. And presumably here we mean in the part 2, right? So in 2015, the skeleton of King Richard III was found under a parking lot in England. Tissue samples from the skeleton contain 93.79% of the carbon-14 expected to found in living tissue. What year did homeboy die? And the half-life of carbon-14 is 5,730 years. So problems of this nature likely to show up on the file, right? We talked a little bit about that. 2 people requested this specific problem, and so if I'm extrapolating, I imagine many of us want to talk about this, which means I would like a little bit of interaction from you guys as we work through it. So first, let me transcribe the important information, and I want you guys to tell me where to begin. So in 2015, King Richard III, skeleton found. Oh, I can't spell skeleton. Was found with 93.79% of the carbon-14 in living tissue. The half-life of carbon-14 is 5,730 years. When did homeboy die? So just the important stuff. In 2015, King Richard III's skeleton was found with 93.79% of the carbon-14 in living tissue. Half-life of carbon-14 is 5,730 years. How long ago did he die? 5,730. Okay. So there are a lot of clues in this question as to the easiest way to set up the problem. What words here signal the kind of exponential function that I'm going to be modeling the carbon-14 content of King Henry III's or King Richard III's skeleton?
It says half-life, so we would know that the B, the thing that's inside the parentheses, is going to be, I'm assuming it's going to be a half.
Very good. Yeah, let's start there. That's perfect. So what Tyson said is perfect. Anytime you see this word or this, I guess, phrase, half-life, remember is this exponential function that chops the output in half every time x goes up by some amount. So we begin with our half-life formula. You could technically begin with any other exponential functions, but beginning with this one where the base is 1/2 is by far the easiest way to set this problem up. Because remember what C and K represent, specifically K. So C is the initial amount. And I actually don't know that here. That's not given to us. But what you'll find is that that's not a problem as long as we have the half-life, which is 5,730 years. So the function that models the amount of carbon-14 x years after King Richard III's death is this one. The original amount of carbon-14 in homeboy's body times 1/2 to the x divided by 5,730. Is everybody comfortable with how we're coming up with this? For example, on the final, this would be worth about 1/3 of the credit for the problem, just getting to this stage. So questions so far? Remember what half-life means. It's the amount of time that it takes for something to decay by 1/2. So every 5,730 years, the amount of carbon-14 in dude's skeleton is reduced by half. Half of it decays through what's called radioactive beta decay. So I've got my function. What am I trying to find?
X.
Yeah, I'm trying to find the x value, which will make this function output 93.79% of the initial amount. So when found, my dude's skeleton had 93.79% of the original carbon-14. So the logic here, this isn't really a math thing, maybe. C, the initial amount of carbon-14, would be the amount of carbon-14 in King Richard III's skeleton while he was alive. That's what this initial amount represents. This is the amount of carbon-14 found in living tissue. We know that there's 93.79% of that initial amount left. In other words, when found, the skeleton has 0.9379 times C. This is 0 grams of carbon-14. So this is the, right here, this is the amount of carbon-14 in the skeleton after X years, right? X years in the ground, homeboy will have this much carbon-14. When they dig him up, he's got this much carbon-14. So what can I do with these two quantities here?
Plug that in for y.
Yeah, that's the idea, right? I want to set this thing equal to this thing. I want to plug this in over here and solve for X. So the problem might seem impossible at first because we're not given the initial amount of carbon-14 in the dude's body, but we're trying to solve for a percentage of that initial amount. So when we set up the relevant equation, here's how much carbon-14 is in the skeleton now. Here's how much carbon-14 would be in the skeleton X years after he died. Both of these have a factor of C, which we can divide both sides by and cancel. So this equation is equivalent to the equation 0.9379 equals 1/2 to the X over 5,730, sorry, not 5,700. There we go. Such equations we'll be able to solve exactly starting today. But at the moment, this was something that we said we needed to solve graphically. And problems solving these things graphically could show up on the final as well, right? A problem where you're required to solve graphically. Maybe they give you the graph, they ask you to sketch the graph, those sort of things.
Sorry, but is this where you could use the log thing to bring the exponent down, the X over 5,730?
That's correct. That's what we're going to learn, but we haven't gotten
Okay.
there yet. So to solve an exponential equation like this by hand, we would need to use logarithms. And it's correct that kind of the reason the logarithm is the appropriate tool is because it will allow us to bring this exponent down. But we haven't discussed the sort of procedure for doing that yet. So at the moment when you've got this homework assignment, the expectation is that you will solve this graphically, like we did with the similar ones in class. So remember the way we do that, we're going to come into our calculator, type y equals, and we're going to enter this for y1, this for y2, and we're going to look for where those graphs intersect. So I'll type parentheses 1 divided by 2, close parentheses, raised to the power of, and you might want to use parentheses up here to make sure you get the whole thing in the exponent, especially if you're on an older calculator. So 1/2 raised to the power of parentheses x divided by 5,730, close paren. There's this function, right? And we can take a look just at the graph of this guy if we want. Obviously, the window settings need to be adjusted here, right? Because this does not look like the graph of an exponential. And the reason for that is because of this 5,730 down here. This is kind of changing the scale quite a lot. Let me We know that we're not interested in negative y values because exponentials are always positive. I can change the y min to something like -1. But let's change our x scales to something like -10 to, why is this not working? Maybe because of a second. Let's change this to something like 5,000. So here we're able to see the decaying side. And if we do something similar on the other side, you'll be able to see the whole expected graph shape for this exponential. We could zoom out more if we wanted, but let's attack the problem. So I need this to be equal to 0.9379. So I type that in for y2, and now I go looking for the intersection point. Oh, looks like it's right in here. So I'm going to zoom in on that portion of the graph. And let's change our y min, y max. Let's make this 2. Something like this. So are we in there? Yeah, it's kind of tough to see, right? We can use the trace function to sort of walk around and try to see where these two are intersecting. We're looking for y to be 0.93-ish. Yeah, looks like we need to go a little further. 938, 93699, somewhere right around here, right? 0.937 is what we're looking for, 9379. Remember, in order to get more granular with this, the tool is to use the table. The trace function will give us a rough idea of where to begin, 537. So I'll go to my table settings by hitting second and then window. I'm going to tell the table to start at like 535 and to increment in a small amount. We want to round to how near? In what year? Yeah, so let me do this in half years, 0.5. So I'm telling my table that the first entry should have 535 for x, and every time I go down one row in the table, x should go up by 1/2. Now let's pull up the table. We had a good starting guess of 535, right? We're looking for places where the column in y1 matches the column in y2, and this is already very close, 0.93733. We want 0.9379. So it looks like we actually need to go back up a little bit. Oh, boom, there it is. Perfect. 0.937. Oh, no, sorry, 39. So we want to go up a little further. There it is. 530 years ago. So graphically, or with the table, we get x equals exactly 530. Am I done?
No.
Not quite, right? As I phrased the question here, I asked how long ago did he die? So the answer would be 530 years ago. But the question as it was phrased in the homework was, in what year did he die? Now the skeleton was found in 2015. So we would have to take 2015 and subtract 530 years. That gets us to the year 1485. So King Richard III died in year, what was it? 1485. Okay. So take a careful look at each of the steps we did here. Think about that calculator work, right? That's where the majority of the actual problem solving takes place, and see if there's anything that you would like to ask. I can bring that table back up. We can ask about the table settings or anything you guys want. Y'all feeling nice and comfy? For a fuller picture of the graph, we can zoom way out. Right? But when we zoom way out, it's actually 530 years is a very small step along this x-axis because I've got the x-mins and max set to 100,000. And that's because this guy is making this function decay very, very slowly. Right? This power only goes up by 1 when x goes up by 5,730. So in order to get a good feel for the picture, we need to zoom way out. But that really wasn't necessary for solving the problem. We just needed to get kind of close, right? Like we started with a guess of around 530 something. And then we got granular with the table, and that's the way to do these. I think we did number 21 last time. Let's take a peek. No, okay, no, we did not do 21 last time. We can do that quickly, and then we're going to move on, okay? So we're told that 7,000 is invested in a bank account with an interest rate of 6% compounded continuously. Okay. How long to reach? How long to reach? Was it 20,000? It's going to be a long ass time. The hint here is the continuously. So remember when we talked about continuous growth rates or something growing at a continuous rate, this was the thing that I said really belongs in a calculus class. But we can set this up. It's not that we can't do the algebra. It's just that it's a little bit tough to explain why we call this continuous growth outside the context of a calculus class. But the function we have for continuous growth was that natural exponential, the base e exponential. And we mentioned sometimes you'll see this as like PE to the RT if you're using t as your variable. Specifically, when you're thinking about investments, they use P for the principal rather than C for the initial amount, but they mean the same thing. So anytime you see continuous growth, you're going to use this guy. We were told that we're investing $7,000. That's our initial amount. And that our continuous growth rate is 6%. So as a decimal, that's 0.06. So this is the function that models the balance in that account, assuming nobody adds or withdraws money, just relying on the interest. So we need to solve this thing equals 20,000. And if we want to, we could begin by dividing both sides by 7,000. And that will give me 20 over 7 equals e to the 0.06x. And then this again is something we would need to solve graphically until we're comfortable with logarithms. So I can come back in here and type in these functions. Remember to type in e, we'll clear this out. To type in e, you hit second and then this divide button. And I have e raised to the power of parentheses 0.06x. And I want to know when this thing is going to be equal to 20 over 7. You could also just type them in as 20,000 and 7,000 e to the 0.06x. But this division would be the first step in solving it by hand. So I think it's a nice thing to do. I didn't clear that. So 20 divided by 7. I'll play with my window settings again. This is not likely the necessary window settings for this. So let's just go back to the standard window to start and see what the picture looks like. Here she is. And again, fairly slow growing exponential here, the 0.06, slowing down the growth of this exponential. Looks like I need to go considerably further to the right. So let's just bump that up by a factor of 10 to 100 and see what we get. There we go. It's pretty much good enough. I can get rid of those big y mins, of course. Again, the exponential function is always positive. Looks like 100 is overkill. Let's go back to 50 here, something like this. All right. Not bad. Again, I'm looking for this intersection point, and I can get a rough idea of where it is using the trace function. Looks to me like it's somewhere around 17. So let's start at 16.1 and go up by 1/10 because they want us to round to 1 decimal. Oh no, 2 decimal places. All right, well, we'll start. Let's say 16.1. And we'll go up at first by just 0.1 to get us a little closer. And then if we need to get more careful, we will. So I changed my table start to that rough value. And I set delta table to a level of precision that I'm comfortable walking around. And if we have to modify that, we can. And then we'll go look at the table. Again, I'm looking for the place where y1 and y2 are equal. Looks like we need to go down quite a bit. Let's see here. 2.8571 is what I'm looking for. So it appears to be between 17.4 and 17.5, right? This y1 is too small. This y1 is too large. So I'm going to refine my guess, the table start to 17.4, and I'll go up by 0.01. All righty, again, looking for the place where y1 and y2 columns are equal. 8571. So again, between 17.49 and 17.5. If we want to know where to round, because they asked us to round to 2 decimal places, we can actually get even more granular. So 5, and we can go up by 0.005 if we want. Table. Again, looking for a place where the y1 and y2 columns match. Here we go. 2.8. 87. No, that's too large. We want 2.8571. 8568. 8577. So yeah, it looks like this 17.5 is going to be as good as we get. 17.495, which one's closer here? 2.8568, 2.8571, 7. So this one is off by, let's see, 1, 2, 3 10,000ths. This one is off by 6 10,000ths. So 17.495 would be a solid answer here. If we're rounding that to the nearest 1 decimal place, that would be 17.5. Nearest 2 decimal places would be 17.49. Let's see, how far off is this? 2.8559. So that's off by 11 10,000ths. Yeah, so 17.5 would be our 17.50 would be our best 2 decimal answer here. Okay. So I do understand that these problems where you have to solve exponential equations graphically, they're not the most fun, right? That calculator business, kind of unsatisfying. The beauty of what we're starting to do is that once you have this mastery over logarithms, you'll no longer need to do any of that graphical stuff. You can certainly verify your work that way, but totally unnecessary because you will know how to solve equations like this completely by hand. And then you can use the calculator to get a decimal approximation by plugging in some expressions. So I want to quickly revisit the idea of an inverse function. If f of x is 1 to 1, then there is an inverse function, f inverse of x, satisfying a bunch of different things. First, the definition was that if you do f inverse after doing f to something, you should just get x back. And also, if you do f after doing f inverse to something, you should get that something x back. This was our definition of an inverse. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. And we had this fact that the point a comma b is on the graph of f if and only if the point b comma a is on the graph y equals f inverse of x. These are the 3 big things that I want to remind you about regarding inverse functions. Of course, a consequence of this bottom one is actually the middle one, right? If all the x's get swapped into the y position, all the y's get swapped into the x position, that's precisely the same saying this. Another consequence is that the graphs have this symmetry about the line y equals x. So I'm going to list that as a separate thing, the graphs y equals f of x and y equals f inverse of x are symmetric about the line y equals x. And the sort of picture here I will draw blue, the original function f. I'm going to draw this to look like an exponential. We added in red here the line y equals x. And then in purple, I will draw the inverse function by taking that blue function and reflecting it over this line y equals x. This is the idea. The purple function has a vertical asymptote here because the blue function has a horizontal asymptote here. And you notice that if you take any point on the blue and kind of flip it across the red dotted line, you land at a point on the purple. That is precisely that symmetry. So these are the three main facts about inverse functions that I need you to be mindful of as we introduce logarithms. The definition we gave last time was that the base b logarithm is the inverse to the base b exponential. If f of x is just b to the x, then the inverse to that function we write as log sub b of x. And really this is an if and only if. We should think about it as being the thing that sends the outputs from this function back to the inputs from which they came, right? That's what inverse functions do. In terms of item 1 up there, this means that if you plug this guy into this guy, or plug this guy into this guy, you should just get x. So that means that the base b log of b to the x, plugging this in here, should be equal to x. And that b raised to the power of the base b log of x will also simplify to x. You can take these as definitions. The easy way to think of it is that the base b log of some number, saying this is equal to y, is equivalent to saying that b to the y is equal to x. Or in words, the base b log of x is the power to which you must raise b in order to get x. It might take some time for you to reconcile in your head the fact that these all really say the same thing. I would argue that the stuff down here is what's going to be most useful for you as you first start working with logarithms and trying to just answer questions like, what is the base 2 log of 16? The definition or properties up here will be more useful as we talk about things like graphing and using logs to solve equations. And solving equations is actually the primary motivation. That is sort of where we go with this eventually, is using logarithms to find exact solutions to the equations that we've been solving graphically. In service to getting us there, though, we do need to practice a little bit with this sort of stuff. Now, I have a worksheet that I am going to work through with you guys partially here today, and then we will work in groups as an activity in our next class. But I just want to show you this resource. I do believe it's in Canvas already for those of you who want it, but where is this logarithm properties? Here you go. So I've had a lot of students who suffer with logarithms and really struggle. This is like your life raft, right? This is actually much better than the homework. Calculus students come to me saying, I forget everything about logarithms. What do? I give them this, they're okay. So I want to work through a handful of these examples with you. You see here the very same definition that I gave here. Let's try. Let's jump to something. So you're going to take each of these expressions and perform the desired thing. So you either want to rewrite in exponential form or evaluate the logarithm or rewrite in logarithmic form. Let's begin with, I'll do parts A, B, and C from problem 1, 2, and 3. I'll phrase this as rewrite as a statement about exponentials. We had log base 3 of x is 9, log base 2 of 8 is x, log base 3 of 27 is x. And log base 3 of 27 equals x. So the intuitive definition here will be more than sufficient. Thinking about this statement up here, how would I rewrite this? Not in like this form, but in like this form. Anybody help me kind of putting this into a form that's like b to some power equals something? What is b here? What is the base we're discussing?
3.
3, right? So when you're talking about logarithms, the base is always this little number down here, the subscript. So this says 3 to some power equals something. What's the power on the left-hand side? 3 to what power? And again, think about this. The thing inside the logarithm is x here, and the thing inside the logarithm is x here. So where does that x end up in the exponential form? It ends up on the right-hand side. And the thing that starts on the right-hand side here, the thing that starts on the right-hand side here is what ends up in the power here. So this says 3 to the 9 equals x. Now 3 to the 9 is a number. We can actually compute that. It's a large number. Get out of this. 3 raised to the power of 9. It's going to be quite large. Yeah, 19,683. We just solved an equation. We just solved the equation, the base 3 log of x equals 9. But this is what they were looking for. They just wanted us to rewrite it as a statement about exponentials, and that is this job done. So we need to practice this until we get very comfy with it. Here, the symbols are in different places. The x is on the right-hand side of the log expression. The base is 2. And the inside of the log is 8. So when we say that the base 2 logarithm of 8 is equal to x, the base b logarithm of x is equal to y, right? This means that 2, the base, raised to the right-hand side, x, is equal to the inside, 8. This is the same as saying 2 to the x equals 8. And you see what the logarithm does is it allows you to go back and forth from statements like this to statements like this. This particular statement here, by the way, kind of easy to work with, right? 2 to what power is equal to 8?
Third power.
Yeah, so here x would be 3. And just evaluating logarithm statements like this, by thinking about them in this fashion, that's really the first skill you need to develop. So it involves going back and forth from one to the other, and then thinking about this guy, right? This is something you know how to think your way through, as long as the number on the right-hand side is a clean power of the base on the left. Let's try it again, this one. The base here is 3, so I'm going to have 3 raised to some power is equal to something. What goes in the power here?
X.
Very good. What goes on the right-hand side?
27.
Perfect. I've heard people describe this as kind of a hook, like 3 to the x equals 27. They kind of draw these arrows hooking things around. If you like that, go for it. And here, again, once we rewrite this in exponential form, we can say what x is pretty cleanly. 3 raised to what power is 27?
3.
Yeah, 27 is 3 times 9, or 3 times 3 times 3, which is 3 cubed. Okay. So you start with some kind of confusing looking thing about logarithms, you translate it into a statement about exponentials, and then all of a sudden you can figure shit out. We're going to practice going back and forth in both directions. Questions on how we got any of these boxed answers here? Okay, let's try something else. Let's take the exponential statements and rewrite them in log form. Okay. Again, we'll just do A, B, and C. So how could I use our definition above here to rewrite this statement, y equals 3 to the 4, as a statement about logarithms? I would ask first, what is the base of the logarithm that we're going to be writing down?
3.
3, right? The base in the exponential, b, is the same as the base of the logarithm here. This b is the same as this b. So this is going to be some statement that starts log base 3 and then of something equals something else. What is the something in parentheses going to be here?
Y.
Very good, right? Very good. This is going to be y, and then this is going to be 4. If I say that the log base 3 of y is equal to 4, that means that 3 raised to the 4th power is equal to y. The log base b of some number is the power to which you must raise that base in order to get that inside. So this says 3 raised to some power 4 is equal to the inside here, and that's precisely what this says. Same again here. If I tell you 27 is equal to 3 to the x, it's going to be a statement about some sort of logarithm. And the base of the log is again going to be the same as the base of the exponential statement. So this is going to say that the log base 3 of something is equal to something else.
Of 27 equals x.
Very good. So it's really all about getting comfortable with this, right? All right, how about this last one? M is equal to 4 squared. That's going to be a statement about a base 4 logarithm. So base 4 of something is equal to something else.
Log 4 of m is equal to 2.
Excellent. Okay. Questions about how to go back and forth from statements about logarithms to statements about exponentials or vice versa? We will get to that sort of stuff, but I would like to do a little bit of raw evaluation first. So yeah, we'll get there. Going back and forth like this is the main thing to getting comfortable. Now that we've had a little bit of practice with that, I'd like to try and evaluate a few logarithms by hand. And after we've had a tiny bit of practice evaluating these by hand, I'll show you what we can do with a calculator. Okay. So here we're not given an equation. We're not told to rewrite this as an exponential. We're told just like find this number. What is this number? The trick, though, is going to be to think about it in terms of an equation. So for each of these that I want to evaluate, I can say, all right, I'm going to let x be this thing. Then I'm going to think about that equation in its equivalent exponential form. and see if from that equivalent exponential form, I can figure out what x is. So how would I translate this now, which is a statement about logarithms, into a statement about exponents?
It's going to be 2 raised to the 4 equals x.
Almost. So I put the x on the left-hand side here, which may be throwing things off. The base is certainly 2. This says 2 to some power equals something. But remember, 4 is like the output from the exponential. The input for the log is the output for the exponential. So the 4 is what's going to go on the right-hand side, and the x is the power. This says 2 to the x is equal to 4. And then from here, this is something we know, right? 2 to what power is equal to 4? Yeah. So x is equal to 2, i.e. the base 2 log of 4 is 2. Nice, right? Yeah, those moments are good moments. There's nothing too mysterious. I think early on, the trick really is just translating into this form and thinking about it a little bit. And you see how being mindful of inverses can be really helpful here, right? Like this is the input for the logarithm, so it should be the output from the exponential, that sort of stuff. So when I say x is the base 3 log of 1/9, what I'm really saying is that 3 raised to the power of x is equal to 1/9. And this one we may have to think about just a teensy bit more. To what power should I raise 3 if I want to get 1/9 out?
Like -2.
Very good, right? So one way you can reason your way here is say, oh, 1/9. Well, that's smaller than 1, right? It's definitely smaller than 3. This power is going to have to be negative, right? In order to have 3 to some power be 1 over something, that power is going to have to be negative. You can rewrite 1/9 as 9 to the -1. And then, 9 is 3 squared. So this is 3 squared to the -1. And then you can say, okay, that's the same as 3 to the -2. So if 3 to the x is going to be equal to 3 to the -2, x has to be -2. In other words, the base 3 log of 1/9 is -2. Let's do the same thing here. If x is the base 10 log of 10,000, that means that 10 to the x is 10,000. So how many times do I have to multiply 10 by itself to get 10,000 out? 10 squared, 10 times 10 is 100. 10 cubed, 10 times 10 times 10 is 1,000. So 10 to the 4, 10 times 10 times 10 times 10 is 10,000. So this means x here has to be 4. In other words, i.e. the base 10 log of 10,000 is 4. All right, you guys do this last one. Someone tell me what do I start with here?
5 raised to x equals 1 over 25.
Very good. So I translate this into a statement about exponents. And then from here, you can either start trying to manipulate the right-hand side like we did here, or we can reason our way there, and there's no harm in that. Certainly, there's a 1 upstairs here. So this is going to have to be a negative power, right, to get 1 over something out from a power of 5. 25.
Would it be -2?
Yeah, exactly. 25 is 5 squared, or 5 to the 2. So 5 to the -2 is 1 over 25. In other words, x here is -2, i.e. this expression, the base 5 log of 1/25 is -2. So you'll have opportunity to practice this in the homework. This is sort of your step 0 in getting good with logarithms, translating into exponents, and then interpreting that exponential or solving that exponential equation, either using techniques like this or just kind of looking at it like this. There are some really fascinating algebraic properties of logarithms, and we're going to explore those. They do interesting things with expressions. But before we're ready to do any of that, we need to look at some graphs, talk about domains and range, and play a little bit with the calculator. In service to that, I need to talk about 2 very special logarithms. These are the natural log, and the other one is called the common log. And each one of these has their own notation. So the log with the base e is very special. In fact, so special that in my field, in mathematics, specifically like number theory, but also a lot of other places, anytime you see a logarithm, you're generally supposed to assume that it is a natural log or a base e log. At the level of math class that we're in right now and through the calculus sequence, we usually write this as ln for natural logarithm or logarithm natural. You can use a script L like this or just a regular straight L, it doesn't matter. If you see ln, that means you're just talking about the log with the base e. The common log used to be a lot more common than it is now, especially back in the day when people had to do calculations with slide rules and whatnot. This is just a special name for the base 10 log. And he gets his own special symbol as well. It can be a little bit misleading because it's just log without any subscript written. So if you see log, but there's no number down here, that means that that number is secretly a 10. Kind of like when you see a radical symbol, but there's no number there, that means that it's a square root, right? That it's the 1/2 power. If you see an log without anything written here, that means that there's secretly a 10 there, and that this is the base 10 logarithm. When we get into things like solving equations and whatnot, I'm pretty much always going to use the natural log. And what you'll see as you move forwards through your math classes is that the natural log is the only log anybody really gives even the 10th of a shit about. All logarithms are in a sense equivalent. And that's the other thing I need to show you before I can get into the calculator stuff, something called the change of base formula. Some calculators do have like an arbitrary log base button, like log base, whatever. But for the most part, you're going to have to translate base 2 logs or base 5 logs or whatever into natural logs or common logs in order to manipulate them in your calculator. This says, given a base C logarithm, to change into a base B logarithm, use the following. Use the formula that the logarithm with the base C of X, so C is like a bad base, for whatever reason, I don't want to use it. I want to use the base B log instead. This is going to be the base B log of X, where B is the base we want to use, divided by the base B log of the old base. So there's kind of 2 degrees of freedom here. C and B could be anything you want. And sort of the point is that we want to go from a base C log into a base B log. The special cases of which we find most useful are changing into the natural log or the common log. Because those are the things we have calculator tools for. So if someone gives you like the base, pi log of 15, and you're like, what the fuck? You can change that into a natural log. It's going to be the natural log of the inside divided by the natural log of the old base. So what I'm doing here is putting B equal to E in the formula above. So you're free to choose B, and I'm choosing to put in the number E for B here, which makes this a natural log, makes this a natural log. The other one, again, somebody gives you a weird base logarithm and you want to change it into, say, the common log. That's done by putting B equal to 10. So we're just about out of time here. In order to show you why this is useful, powerful, good, let's revisit to the problem that we saw when we first talked about logs. This is approaching the equation solving stuff. So what follows here, the thing I'm going to do right here, we're going to talk a lot more about this on Thursday. The trick is I can rewrite this as a log statement. 2 to the x equals 3 can be rewritten in logarithmic form as x equals the base 2 log of 3. Remember this, we looked at this equation graphically, we were able to justify that there should be a unique solution somewhere in the 1.5-ish range. Well, here is that solution. It's the base 2 logarithm of 3, and it's just straight up from the definition. By definition, x is the base 2 log of 3 if 2 to the x is equal to 3. But the fuck is this number? Well, you can use your change of base formula and the natural log button on your calculator. By the change of base formula, this is the same as the natural log of 3 divided by the natural log of 2. And later I'll show you how you can sort of get to this form right away rather than going through this. But for now, this works. I come in here, I type natural log of 3, close that parentheses, divide by natural log of 2, close that parentheses, 1.5849, blah, blah, blah. So I call it 1.585. The catch here is that these two are exact answers. This decimal over here is an approximation. Logarithms are what are called transcendental functions, meaning the numbers that they output more often than not are irrational. And I don't mean like square root of 2 irrational, I mean like pi irrational, like fucking weird ass numbers. This is an example of a fucking weird ass number. Right? It's not nice in the sense that like 5 or -1/2 is nice. There is no way to write this as a fraction of whole numbers. There's no way to write it as a power of a fraction of whole numbers. It's just ln3 over ln2, or the base 2 log of 3. But I can verify that if you take a number that is about this size, like 1.585, and plug it in here, so 2 raised to the power of 1.585, this should come out very, very close to 3. And indeed, 3.0000, and then some other shit, exceptionally close to 3. Moving forward, we're going to be deeply concerned with solving equations like this, right? You might notice this is very similar to the equations that we were looking at the start of class. So like, 0.97 equals 1/2 to the x over 5,000. It's like some exponential function equals some constant. These are called exponential equations, and the primary tool for solving them is logarithms. We will develop much more sophisticated methods than just going, oh, this is equivalent to this by definition, because we'll want to solve more sophisticated equations than this, but this is where it will start. The other thing we're going to do is talk a lot about graphs. So learning the graph of logarithm functions, domains, ranges, asymptotes, intercepts, all that shit is going to be very, very important as we move forward. That is all I have for you guys today. I hope you found today a little bit exciting. I think this logarithm stuff is very, very cool. Make sure you put the time in here. This is sort of considered the harder part of this class. As we move forwards, we'll be talking a lot about algebra properties of the logs, not just graphs, but the sort of kind of like rules for exponents, but rules for logs. And those will be important in solving the more complicated exponential equations that we have. Any burning questions for me before I let you guys go? Okay, activity next time. So remember to show up on time. Remember to participate in the activity. I have had some folks kind of showing up on those days, but then when I like try to check in and be like, hey, how you doing? What you working on? I get nothing, or some people who aren't even joining the breakout room. So please, when you come on activity days, make sure you participate. I cannot give you credit unless you do. If you have any questions for me, anything you want to talk about, office hour today from 11 to 12, or you can send me an email or Canvas message. I got a little bit behind on my email, so if you're waiting for a response from something, either over the weekend or yesterday, please bear with me a little bit. If something is urgent, feel free to come by an office hour, or you can blow up my inbox if you have to. If you need a reply right away, you send a message 2 or 3 times. I promise I'll get to it. Otherwise, just be patient. Things will come down the pipe. I've got like 20 emails I need to get through this morning. That's it from me. Take care, guys. I'll see you on Thursday.